Hello, everyone. Thank you so much for taking the time from your busy schedules to attend our topic. I'm honored to present to you today a technical sharing about the gap between WebAssembly and JavaScript in V8. First, let me briefly introduce ourselves. I'm Nan Wang, also known as Sakura in the security community, focusing on Chrome vulnerability research. I have been a top researcher in the Chrome VRP for past 4 years and ranked second in Facebook's Bug Bounty Programmer in 2023. I have also spoken at major security conferences, including Black Hat USA and Asia, and ZeroCon.
Okay, hello everyone, and my name is Zhanghang Xiao, and is a master student at Tsinghua University, and is an inter-security researcher on serious tech. And I specialized in browser security and fuzzing techniques, and is also a top Chrome VRP researcher. And I have spoken at Black Hat USA and ZeroCon. As a representative of Serious Tech, I'm honored to introduce our company. We are innovative cybersecurity firm focused on integrated offensive and defensive security solution. The company specialized in attack behavior modeling, threat intelligence, and cybersecurity services, as well as security assessments and attack defense simulations to help organizations strengthen their security. By combining AI-driven technology with advanced analysis, the company provided intelligent and comprehensive security solutions for enterprises.
Now, let's dive into today's core topic. Here's our agenda, covering key attack surfaces in WebAssembly and JavaScript. We'll start with a brief introduction to the research background and our motivation for choosing this direction. Then we'll analyze several vulnerability patterns about WebAssembly and JavaScript. Finally, we'll summarize our key findings, discuss possible mitigation strategies, and outline future research directions. First, let me briefly explain why we chose WebAssembly as a focus of our research. Over the past year, we conducted a systematic analysis of exploitable and public disclosed WebAssembly-related vulnerabilities in the stable version of Chrome. One key observation is that these vulnerabilities are not only featured in high-profile security competitions like V8 CTF and Pwn, but also actively exploited in the wild, highlighting WebAssembly as a growing target for attackers. A critical concern is that WebAssembly remains in rapid development with new proposals and features being introduced regularly. This makes it likely that more vulnerabilities will appear in the future. Let's take a look at this simplified diagram. Between these two runtimes, there is a crucial bridging layer referred to as wrappers, which consists of JS to Wasm and Wasm to JS wrappers. These wrappers handle critical cross-language interactions, including import and export. Our research focuses on this interaction boundary as it's a high-risk area where vulnerability can occur. With the continuous evolution of WebAssembly, including new features like GC and JSPI, this interaction layer is becoming more and more complex and introducing new security risks. In this section, we'll recap the overall architecture of our grammar-based JavaScript Fuzzer, which played a key role in finding the vulnerabilities. As shown in the diagram, on the far left is the sample hoppers, which contains our initial set of JavaScript code samples. A common misconception in fuzzing is to randomly insert or mutate these samples blindly. Purely random mutations often lead to code that fails basic syntax checks or contains semantic errors. For instance, random changes might result in invalid type operations like treating a string as a function or accessing variable in the wrong scope, such as referring undefined variables. These mutations are many but not useful. To address this, we incorporated 3 key analysis techniques into our Fuzzer's analysis layer. Type analysis, this helps track variable types. Scope analysis, this makes sure variables are used correctly in their lifecycle and visibility. Context analysis, this finds the right syntax or API calls for the execution environment. Making code generation more meaningful, this analysis results guide the mutation engine to create valid test case. With this foundation in place, let's dive into the first core part of our research, type confusion between WebAssembly and JavaScript object. Okay, this vulnerability pattern has not only been discovered by us, but have also appeared in the wild and in CTF. Our research uncovered two high-risk vulnerabilities, both caused by type confusion between WebAssembly and JavaScript objects. But firstly, let's explore the WebAssembly GC proposal, a key background concept for understanding these vulnerabilities. This diagram compares two WebAssembly modules, the traditional MVP models with its linear memory management and only numeric types, while the new GC proposal introduced object modules, struct and array types, and automatic garbage collection, which simplified development but creates new security risks when interaction with JavaScript. In the slide, we explore a key question. Is the JavaScript runtime fully prepared to handle WebAssembly GC objects? To systematically investigate this, we enhance our type-aware fuzzer with a targeted mutation strategy. We modified the fuzzer to randomly replace normal JavaScript objects, such as the normal proto object in the bottom left screen, with exploited WebAssembly GC objects from Wasm runtime. The result is there are multiple crashes. Now, let's introduce the fuzzer type confusion vulnerability, which is triggered in a very simple way. On the left, we see two key lines from our POC, where a WebAssembly object is inserted into a JavaScript object's prototype chain. As shown in the right diagram, where it does not enforce any restrictions on the assigned value, meaning any WebAssembly object can be set as a prototype for a JS object. The vulnerability triggers through the following steps. First, an attacker inserts a WebAssembly object into the prototype chain of JavaScript arrays. Next, when JavaScript code performs an array concat operation, V8 invokes slow array concat, which intercalls iterator elements to traverse and process the array elements. During traversal, V8 checks elements type by calling has only simple elements. The issue arises in has only simple elements. As shown in the source code snippet on the right, the function iterates through the prototype chain, but critically, it only checks whether an object is a JS proxy. If the object is not a proxy, the function blindly assumes it is a JS object and forcefully casts it. However, if Wasm object is reached during iteration, this assumption breaks. The incorrect type casts mismatched memory layouts, leading to type confusion. This slide presents Chrome's fix for this vulnerability, which follows a clear security principle. It explicitly checks for JS objects type rather than merely avoiding JS proxy types. As shown in the code patch on the right, the fix modifies the type check in has only simple elements. Now, let's analyze the second type confusion vulnerability. This vulnerability occurs in V8, the JIT compilation optimization process. As shown in the flowchart, this bug is related to JavaScript's instance O operation. During optimization, compiler attempts to speed up instance O checks by calling try-build faster instance O, which in turn invokes the build has in prototype chain to determine whether the object's prototype chain contains the target constructor's prototype. During compilation, in info has in prototype chain, it executes the code prototype as JS object, which assumes that prototype is always a JS object and directly casts it as JS object. However, this assumption fails when prototype is actually a Wasm struct. Chrome's fix for this vulnerability follows a similar approach to the previous vulnerability by hardening type checks. Now, let's explore another critical WebAssembly-related vulnerability, type confusion in store inline cache handling. This vulnerability was discovered internal by Google's cluster fuzzer, and it shares the same vulnerability pattern as the two vulnerabilities we identified. In V8, property assignment triggers the store inline cache mechanism, optimizing execution based on observed object types. Store IC has 3 states, monomorphic with a single object type for highest efficiency, polymorphic with multiple cache types for quick lookups, and magmorphic, which uses a slower generic path when too many types are observed. WebAssembly objects are designed to be opaque, and setting properties on them should trigger errors. The problem arises because update cache is called before object set property. This means that even if a property assignment operation fails, store IC already records the WebAssembly objects map. Next, let's walk through a complete exploit to demonstrate how this vulnerability is triggered. The first stage involves training the inline cache system. To do this, we repeatedly invoke a function that sets property on a normal JavaScript array. Prompting the V8 to optimize this operation using store IC. At this point, the IC is in an uninitialized state, merely collecting feedback about the types of object being used. Second, we set a property on a WebAssembly array and catch the expected error. Crucially, the IC now incorrectly caches the WebAssembly object's type, despite the failed assignment. Thirdly, we perform more property assignment on normal JavaScript arrays. This adds a second type to the IC, transitioning it to a polymorphic state, where the same handler is incorrectly used for both Wasm array and JS array operations. Finally, we trigger the exploit by setting a property on the WebAssembly array again. The IC now processes this. Along the fast path designed for setting elements on normal JavaScript arrays, results in an OOB access. This exploit highlights the delicate interaction between V8's optimization mechanism and WebAssembly integration. So what is the impact of this vulnerability? The right side of the figure simply shows the structural differences between JS array and Wasm array. In the Wasm array memory layout, the third 4-byte field represents the array's length, while in JS array, the field represents a pointer to the elements array. In the script shot on the left, we observe a Wasm object with an initial length of 0. When the incorrect store handler executes, it unexpectedly updates this length field with a pointer to a real data fixed array. As a result, the length of what was originally an empty Wasm array is changed to an extremely large value. This allows us to use this Wasm array for almost arbitrary out-of-bounds reading and writing, making it truly easy to achieve remote code execution. The root cause of this issue lies in V8's insufficient type checks when performing property assignments. Previously, V8 only applied special handling for JS proxy objects, while failing to account for other non-JS object types, such as Wasm objects. This override allowed Wasm object to incorrectly optimize the execution path meant for JavaScript objects. The patch directly addresses the issue by hardening the type check. Now, we'll turn to another serious security vulnerability related to WebAssembly, the use after free issue in V8's WebAssembly internal function garbage collection mechanism.
In our previous analysis, we studied how WebAssembly objects and functions can be exported to JavaScript for direct use. Now turning our attention to the reverse situation, we are focusing on the security risks that arise when WebAssembly calls imported JS functions or objects. This slide further refines our fuzzing strategies, specifically focusing on testing the interaction between WebAssembly and JavaScript through the import section. The diagram on the right illustrates the 3 key components of this process. The first component is the WebAssembly import declaration. This defines an imported function from the JS namespace, which allows us which allows the WebAssembly to call a JS module, to call a JS function as if it were a native function. The second component is the JavaScript export function. Here we create a WebAssembly function that invokes the imported JavaScript function and then export it, enabling JavaScript to call this function and trigger the execution of the imported function. The third component is the instance creation and the import objects. During instance, we provide a random concrete JavaScript function implementation, which in this specific example simply calls the GC function once. Through this modification, Fuzzing can test more cross-language call scenarios. In other words, we are making the Fuzzer focus on not just on pure JS or pure WebAssembly logic, but specifically increasing mutations for JS function imported into WebAssembly, automatically generating various unusual function signature parameters and dynamic call scenarios to discover potential cross-language vulnerabilities. Now, let's take a deeper look at the root cause of this vulnerability. When a JavaScript function that triggers garbage collection is imported into WebAssembly using a WebAssembly function, V8 initially handles the call through a general Wasm2JS built-in function, ensuring that the basic functionality works correctly. However, if JIT function or similar optimization flags are enabled, V8 may trigger its setup mechanism during execution, recompiling and optimizing the function. This process updates the Wasm internal function code field to point to the newly optimized Wasm2JS wrapper. The critical issue arises when garbage collection is triggered again during the execution of the JavaScript function. V8's garbage collector scans and updates various object references, but it fails to properly track and update the code field of Wasm internal function. If the memory location referenced by this field is moved or is freed during garbage collection, but this pointer itself is not updated, WebAssembly may later attempt to execute code at an invalid or recycled memory address. Let's examine Chronos fix. The key change tells its garbage collector to track the code field in Wasm internal function as strong references. Next, we'll introduce attack services we identified within WebAssembly JSPI. JSPI, or JavaScript Promise Integration, is a significant new feature in the WebAssembly ecosystem that bridges the gap between WebAssembly and the JavaScript's asynchronous programming model. However, this new interaction boundary also introduces new opportunities for exploitation. First, let's introduce JSPI. In JavaScript, asynchronous programming is fundamental. When calling functions like fetch to request network resources, we expect the operation to be non-broken, allowing the browser's main thread to continue processing other tasks instead of waiting for a response. This is why many time-consuming operations in JavaScript return a promise, which represents future results that will be resolved once the operation completes. However, this presents a fundamental challenge. WebAssembly's execution model is entirely different from JavaScript's. WebAssembly follows a synchronous execution model similar to C, and does not natively support asynchronous operations. So what happened when a WebAssembly module calls JavaScript functions that returns a promise? How does WebAssembly handle such an asynchronous results? This is precisely what JSPI aims to solve. enabling WebAssembly to seamlessly invoke asynchronous JavaScript functions and properly handle promises. Now we understand the challenges JSPI faces. Let's examine how it addresses them. Proposed in 2024, JSPI introduces an innovative mechanism that allows WebAssembly codes to synchronously invoke synchronous JavaScript functions. The JSPI workflow operates as follows. When WebAssembly calls an asynchronous JavaScript function, instead of immediately returning a result, the function returns promises. At this point, JSPI suspends WebAssembly execution and transfer control to the JavaScript environment, where the asynchronous operation continues. Once the operation completes and the promise is resolved, JSPI resumes the suspended WebAssembly execution context, passing the resolved value back to WebAssembly so it can continue execution. From WebAssembly's perspective, this entire process appears as a normal synchronous function call, even though it actually spans an asynchronous boundary. So this seemingly straightforward mechanism invokes complex execution stack management. When WebAssembly execution is suspended, the entire execution context, including stack frames and local variables, must be preserved. Meanwhile, JavaScript's micro-task queue tasks over to process the asynchronous operation. Once the promise is resolved, the saved WebAssembly execution context is restored, and the execution resumes from where it's left over. To facilitate the complex interaction between WebAssembly and JavaScript, JSPI introduces two key interfaces, WebAssembly suspending and WebAssembly promising. WebAssembly suspending acts as a function wrapper for JavaScript's asynchronous functions before they are imported into WebAssembly. Its purpose is to add the necessary logic to handle execution context, switching, and suspension when WebAssembly calls these functions. WebAssembly promising is another wrapper used when exporting WebAssembly functions to JavaScript. If a WebAssembly function internally calls an asynchronous JavaScript function, it must be wrapped with WebAssembly promise when exported to JavaScript. This ensures that JavaScript receives a promise object instead of blocking the execution thread when calling the WebAssembly function. The diagram on the right illustrates how these two interfaces work together. The upper process shows how an asynchronous JavaScript function is imported into a WebAssembly module using WebAssembly suspending and invoke within WebAssembly. The lower process demonstrates how a WebAssembly function utilizing an imported asynchronous function is exported via WebAssembly promising and called from JavaScript. Now, let's explore how we use JSPI to identify potential security vulnerabilities. Our fuzzing strategy focuses on JSPI-specific modifications and test case generation. As shown in the diagram, we take existing WebAssembly JavaScript code and adapt it to leverage JSPI by wrapping exported functions with WebAssembly promising, adjusting instantiation parameters and crafting test scenarios that activate JSPI mechanisms in different execution states. The lower section illustrates this transformation. We start with standard WebAssembly code and introduce JSPI-related constructs such as D8s. We test enable JSPI and WebAssembly promising to create JSPI-enabled test cases. Next, we'll discuss the vulnerabilities we discovered in JSPI. We found that V8 handles imported JS functions different from native WebAssembly functions within its WebAssembly-related logic. Specifically, V8 use Wasm API function refer to store metadata for imported JS functions, while Wasm trusted instance data represents native WebAssembly functions. Now we aim to explore a critical issue, whether it is possible to cause V8 to misinterpret two distinct internal structures. If we can find a scenario where V8 mistakenly treats one as the other, we may discover a way to exploit type confusion. This is exactly what this vulnerability exploits. In this case, we attempt to import a JavaScript function into WebAssembly, then export it back to JavaScript, and finally use this exported function with WebAssembly promising to see if any issue arises. As shown in the right diagram, invoking V3 in our POC indeed triggers a type confusion bug. When V8 executes the function returned by WebAssembly promising, it first set up the core targets and prepare the necessary arguments inside the Wasm promising wrapper. However, the problem arises because Wasm promising does not recognize that the input WebAssembly function is actually just a discussed JS function. As a result, when preparing core arguments, it pushes Wasm trusted instance data object onto the stack, while the actual core target expects Wasm API function refer, which represents the JS function. This mismatch leads to type confusion. To assess whether this type confusion could have broader impacts, we examined the internal fields of these two structures and made some interesting discoveries. In Wasm trusted instance data, certain pointer fields are protected, meaning they do not point to objects within the V8 heap, but instead reference separates isolated memory region. We refer to this as the trusted memory region, which stores sensitive information and is deliberately separate to prevent exploitation by attackers. As shown in the diagram on the right, we can observe the internal layouts of both structure and the relationship between key fields. Notably, the callable field in Wasm API function refer and the dispatch table for imports field in Wasm trusted instance data shares the same offsets. Yet they have different meanings and point to distinct memory regions. This scenario leads to fascinating consequences. What happens if Wasm trusted instance data object is misinterpreted as Wasm API function refer? As shown in the diagram, when the field data remains the same, the change in object type causes the callable field in Wasm API function refer is to be treated as pointer to point to an offset within the V8 heap at addresses 11223344. This means that if we carefully manipulate the V8 heap layouts in advance, we can ensure that the callable field of the confused object points to controlled memory region. As a result, we can construct a fake callable object within the V8 heap. With this fake callable object, we gain a powerful exploitation primitive. Since callable objects represent executable functions in JavaScript, controlling one allows us to manipulate execution flow and potentially leading to further exploitation. Here, we provide some screenshots demonstrate the exploitation process. As shown, after using an array field with floating point number to shape the memory layout in the V8 heap, triggering the type confusion vulnerability allows V8 to interpret our crafted data as callable objects. In this captured output, the RCX register contains parts of the binary representation of the floating point number 1.1. confirming that our controlled data is being treated as function references. The fix for this vulnerability was remarkably simple. By imposing certain restrictions on functions imported from the JavaScript side, the issue was effectively resolved. As shown on the right, the patch restricts the functionalities of JavaScript imported functions used within WebAssembly. Specifically, it disabled the generic JS2 Wasm wrapper for imported functions. Since JSPI strengthens the connections between JS and WebAssembly, does it also introduce potential issues in compilation optimization? So this is precisely where the vulnerability we discovered lies. However, before diving into the details, we need to understand some background information. To enable JS and WebAssembly execution context to invoke functions from the other side, a glue is required to convert data types between the two environments. This is the role of function wrapper, which plays crucial parts in ensuring the correct transformation of data and control flow across different language contexts. Depending on the core direction, wrappers are categorized into different types. For example, Wasm2JS wrapper is needed when WebAssembly calls a JS function. A JS2Wasm wrapper is required when JS calls a Wasm function. And JS2JS wrapper is used when JS calls a function exported from WebAssembly that originates from the JS side. In this diagram, we illustrate the relationship between different wrappers and components. As shown, when a JS function is about to import it into WebAssembly, it must first be wrapped by a Wasm2JS wrapper. This ensures that when WebAssembly calls the imported JS function, the wrapper correctly converts WebAssembly types to JS types and vice versa. Let's take a closer look at how the V8 engine optimizes this performance of these wrappers. The general JS2 WebAssembly wrapper is designed to handle various type conversion scenarios, but this flexibility comes at the cost of efficiency. When a WebAssembly exported function is frequently called, the overhead of these conversions become noticeable. So the general wrapper needs to be optimized to speed up the conversion process. In this diagram, we illustrate how frequent calls from an external JS function to a specific WebAssembly exported function triggers with compilation optimization, generating an optimized version of the wrapper, which we refer to as a tied-up wrapper. This optimization focuses on improving parameter conversion efficiency and reducing invocation overhead. Interestingly, this optimization mechanism not only affects frequently called functions, but also impacts other functions with the same function signature. As shown in the diagram, although the external JS function primarily calls WebAssembly function B, the optimized wrapper also replaces the wrapper for WebAssembly function A, even though A has not yet triggered compilation optimization. This shared optimization mechanism is based on function signature similarities. When two functions have the same parameters and return types, we assume they can share the same optimized wrapper, which is generally an effective resources utilization strategy. However, as we will see, this sharing mechanism can also introduce potential security risks. Now let's understand its optimization mechanism for its exported function wrapper. We can consider interesting questions. What happens if a JavaScript function is first imported into WebAssembly and then exported back to JavaScript? How does this circular import-export pattern affect wrapper selections? The answer is quite intuitive. In this case, since the final call chain goes from JavaScript to JavaScript, with WebAssembly merely acting as an intermediary, the wrapper used is JS2JS wrapper. This makes sense because both the caller and the target function are in JavaScript, even though the function undergoes an import into WebAssembly before being exported again. Now we arrived at our critical issue, considering a scenario where a function exported from WebAssembly is actually a JavaScript function that was previously imported into WebAssembly. This function is wrapped using a JS2JS wrapper. At the same time, its function signature matches that of our natively exported WebAssembly functions. When V8 applies the wrapper optimization mechanism discussed earlier, a serious issue arises since V8 optimized wrappers based solely on function signatures. It replaces all wrappers with matching signatures with the optimized title wrapper. As a result, the function that was supposed to use JS2JS wrapper is incorrectly replaced with a wrapper optimized for native WebAssembly functions. The crash happened because the title wrapper is specifically designed for converting JS types to WebAssembly types. However, in this case, it is mistakenly used for a JS2JS core, where the underlying handling logic is entirely different. This slide presents the POC for the vulnerability and its crash error messages. In this POC, a JavaScript function with I32 parameter is imported into WebAssembly and later re-exported, receiving a JS2JS wrapper. Meanwhile, a native main function with the same signature is also defined in WebAssembly. By repeating calling main, V8's optimization mechanism replaces all matching wrappers, including the JS2JS wrapper, with an optimized title wrapper designed for native WebAssembly functions. This mismatch leads to a type error and memory access violation, ultimately causing a crash. So the highlighted code illustrates key components: defining the function signature, importing the JS function, re-exporting its defining main, and triggering optimization through repeating calls. The fix for this vulnerability is straightforward. Similarly to the previous ones, when replacing wrappers for WebAssembly exported functions, the solution ensuring that if WebAssembly was originally imported from JavaScript, its wrapper is not replaced. Finally, let's summarize the enhancements we made to the JS function fuzzers and how they contribute to discovering new types of vulnerabilities. Previously, the fuzzer primarily focuses on JS syntax and type mutations with limited handling of WebAssembly JS interactions. To address this, we introduced several key improvements. The first, we enhanced the fuzzing of WebAssembly imports to JavaScript. Now, the generated WebAssembly module can export objects such as arrays and structures to JS, randomly replacing native JS objects like array and objects. This increases the likelihood of triggering type confusion and memory safety issues, which traditionally JS only fuzzing often miss. Second, we extend fuzzing to JS imported into WebAssembly by passing JS functions, including regular and asynchronous functions into WebAssembly as imports and performing randomized calls and mutations. We can thoroughly test the WebAssembly to JS core bridges. This helps uncover potential memory corruptions, vulnerabilities caused by improper reference management or incorrect type checks. Finally, we introduced JSPI mutation by leveraging WebAssembly promising and WebAssembly suspending to automatically insert and modification synchronous boundaries. Since many JS engines still have incomplete implementations of JSPI features, this approach exposes previous unknown security flaws. In summary, our research highlights key security risks at the WebAssembly JavaScript boundary. New features like WasmGC and JSPI introduce potential vulnerabilities, making the boundary a critical focus for security risks, for security research. JSPI enhance serious integration, but increase risks such as type confusion, GC management issue, and execution stack switching, requiring a careful balance between security and convenience. Fast testing remains crucial for uncovering vulnerabilities and integrating JSPI wrapper functions into type-aware fuzzing system enables the discovery of issues beyond traditional JS-only or WebAssembly-only testing. As WebAssembly proposal advanced, boundary security must remain a priority. And that's all. Thank you for your listening.
Thank you.